Okay. So now I want to talk about, now that we have this nicer language set up, I want to talk about positive geometries and canonical forms. And I won't talk about fancy positive geometries. I'll just talk about here just polygons and polytopes in general. But first, let's set things up by talking about some simple motivating examples. So our first example of a positive geometry or a polytope is a line interval. Okay, so it's one-dimensional, and so I have the lovely space between 2 points A and B. Okay, and so this is a space, and I want to sort of talk about that interior, that region between A and B. All right. So first, let's talk about this in the most obvious way. So here I have some coordinate, I don't know, z, and so what is every point in there? Every point in here is of the form some W1A plus W2B, some weighted sum of W1 and W2, right? Where W1 and W2 are positive. So if you want to give me all the points between A and B, they're all some weighted sum of A and B. Is that clear? So W1 and W2 are just any old positive numbers. Now, let me say this statement projectively. Okay? So projectively, I want to think about all these things as two-dimensional vectors, right? And again, if in this simple case, we might as well do it. If I go back to the underlying picture of like lines through the origin in 2 dimensions now, okay, so here is a line through the origin corresponding to the point A. Here's a line through the origin corresponding to the point B, right? Then all of these things are just any line through the origin that goes between A and B, right? And so any such vector on this line, any such vector on a line like this is just any old positive linear combination of A and B. I don't have to put any restriction on it. Like here I have to put a restriction, the weights added up to 1, which is why I divided by W1 plus W2. But here clearly I can take any positive linear combinations of A and B that'll give me some other vector that lives in there, that'll be a point on the inside of this interval. Right? So if I say this projectively now, there's some capital Zi. Now I runs from 1 to 2. And capital Zi is like some W1 AI plus W2 BI, where now, and I don't have to divide by W1 and W1 plus W2, where I just say W12 is positive. Okay? Geometrically, the way you'd say it is that there's really a cone here, right? There's A and B. This space in the one higher dimension is really the inside of this kind of cone. In this case, it's just a triangle, but it's the inside of that cone. And when I slice the cone with the plane at infinity, I get the inside of this interval. Okay? And once again, algebraically, you don't have to think, you don't have to draw pictures. It's just obvious, right? That if A looks like 1A and B looks like 1B, then W1A plus W2B is equal to W1 plus W2, W1A plus W2B, which is equivalent, after rescaling this to 1 times this thing that we had before. I apologize for running out of room there. Okay? Okay, is that clear? So, all right. And that notion clearly generalizes. Okay, so if you give me, so if you give me a bunch of points, now I'll switch notation to amplitude-friendly notation. So let's say I'm on the plane, and now I have some point z1i, z2i, z3i. Then I can look at all the points y that are some linear combination of these guys with the c's positive. OK? And all these points are just spanning the inside of this triangle. Right? But I could keep going. If I had 4 points, if I put a 4th point here, okay, then this formula, which is just the weighted, not non-weighted, just positive sum of the external data, gives me the interior, or the convex hull of all the vertices. Now, I should caution you that every time you draw a picture like this, see, every time you draw some two-dimensional picture in this case, and you say, I'm thinking about things projectively, then when you uplift to one higher dimension, you're always drawing a picture where all the points that you have in your picture are on the same side of some plane, right? So, for instance, take any of these pictures. Any of these pictures, when I add one higher dimension, there'd be some z1 here, z2, z3, z4. I'm kind of intersecting with this plane here to get the picture of some kind of quadrilateral there. Okay? But it's very important they're all pointing this way. They're all on the same side of some plane like this. Okay? That's guaranteed. It's guaranteed by our construction. In other words, when I start from a two-dimensional picture and I uplift to 3 dimensions, I'm doing this by adding 1 to the top component of all the vectors. Adding 1 to the top component of the vectors means that there is a plane, 1, 0, 0, 0, such that all of these points are on the same side of that plane. Right? That's good. So when that's the case, then a positive combination of the external vectors just covers the convex hull of the corresponding polygon or polytope that you have. Okay, so there's always, thinking in terms of the vectors, it's really a cone. There's a whole cone that you can slice in many ways to get polygons or polytopes of different shapes. These things are related to each other just by doing GL3 transformations, SL3 transformations. Different SL3 transformations will move the vertices around, okay, but that's just taking the same cone and slicing it with different planes. Okay? But it is very important, but it's not always true backwards. Okay, so if someone hands you a bunch of vectors and says, look at this combination, it is not guaranteed that that's well defined. In order for this to be well defined, it's very important for the left-hand side to never be able to go to 0 projectively. Okay? And that's not guaranteed. If you give me a whole bunch of z's, it's possible for the linear combination of them to add up to 0. So let's do so if I go back to a one-dimensional example, something that's good is just like what we drew, an A and a B. And I can even imagine a C there, but this would all be fine, right? All of these guys are on the same side, and the convex hull of all these points would just be that interval. But this is something that will be bad, A, B, and C. Okay? If I take positive linear combinations of these guys, I just get the whole plane. And the formula C dot Z is not well defined projectively, because somewhere, for some C's, the Y can go to 0. Right? So I'm just cautioning you that if someone hands you a random collection of vectors, it's not guaranteed that they're associated with a one lower dimensional polytope projectively. And the opposite direction is always guaranteed. If someone hands you a polytope, you can always turn it into a cone. Okay, by adding a 1 to the top component, which guarantees that they're on the same side of a hyperplane and taking their positive combination. Okay, so far so good?
Question?
Yes.
So for that C, if we're in projective space,
Yes.
shouldn't we identify it just with the whole line?
That's a problem. That's exactly the problem. So if we take so I'm just saying that the formula, this formula, y equals c dot z, is not projectively well defined because a linear combination of these guys can go to 0. So exactly that picture does not allow me to make this statement projectively meaningful. And you can see that if I do take the positive linear combination of all these guys, I just get the whole plane. I don't get anything. Yeah. All right. Anyway, that was a side comment. I just wanted you to be aware that it goes one way, but not the other. Okay. But now we have defined, if you give me any collection of, let's even just do polygons, okay? At least I've defined what I mean by the points on the inside of this, the points on the inside of this polygon are all, projectively are all things of that form, okay? So this is our first slightly, so that's in 2 dimensions. Just in 1 dimension, if I just had some z1 and a z2, then it's just something of the form y equals c1 z1. Oh, by the way, I could also have points on the inside, right? That would also be fine, but not all the points in this formula are guaranteed to end up as vertices of the object. Some of them could be inside. And so this is another example. In 1 dimension, I could have a whole bunch of other points in there, z1 plus z2 plus all the other ones. But these are both things that give me nice geometric regions. Okay, and I can define the nice geometric regions as a positive combination of a bunch of external data. Okay, so this is the first appearance of the notion of positivity. The positivity and interiors are connected to each other. Right? I want to talk about the inside of some region. It's associated with a certain notion of positivity. Is that clear? So that's the, okay. So far so good though. We've managed to get some geometric shapes. That's perfectly fine. But now we would like to do more. Now I want to tell you about this notion of a canonical form. And to talk about the canonical form, let's go back to the 1-dimensional example. So again, let's say I have A and B. I'll go back to doing it in the old-fashioned way with just some coordinate z. Okay? And now I'm going to associate with this interval. You see, this is a real geometry. I'm going to associate with this geometry a certain 1 form. It's a 1-dimensional geometry, so I'll associate a 1 form. And the 1 form is just going to be dz over z minus a minus dz over z minus b. Okay, or I could write it as dz b minus a over z minus a z minus b. Okay, what is special about this form? What's special about it is that it has the canonical singularity dz over z, singularity that has a residue that you can calculate and detect by taking by computing a residue. That's often called a logarithmic singularity because you can write it as d log z, right, in the neighborhood of the singularity. This form has a logarithmic singularity at z equals a and another logarithmic singularity at z equals b, right? Okay? Now, why did I put a minus sign here? Anyone have a guess?
Infinity.
Albert, you're the last person I wanted to answer this question. Perhaps literally. Anyone other than one of the great mathematicians of our time wants to answer this question? But you answered it already. So, yes, the answer is that there would otherwise be also a pole at infinity, right? So if I put a plus sign here, then this form would have singularities here and there, but it would also have another singularity at infinity. And infinity is not part of my picture, right? So this already shows the basic point, is that I want a form that has logarithmic singularities on the boundaries of the space, and only on the boundaries of the space, nowhere else. Okay? Is that clear? So that's why I put the minus sign there. All right. Now we can write this in various other, so let's just practice. Let's just play. So let me write this, for example, I could write this omega, I can write it as d log z minus a minus d log z minus b. That's equally correct. It's d log z minus a over z minus b. Write it in all trivially correct. And notice the whole thing has an ambiguous sign. There's an orientation with the whole thing that I have to decide. So that's not God-given, whether a z minus a or z minus b or the other way around. The overall sign is not fixed, but the relative signs are fixed. Okay? Okay, but now let's talk about this projectively. So projectively, I want to now have some capital Z variable and some capital A and some capital B. Okay, so I'm going to have some capital Z I and AI and BI as the ends of my interval again. A, B. Okay, and so let me first write down the answer, but then we'll talk about it a little bit. This one form is Z dz AB over ZA ZB. I'm reverting to my Canadian self by calling it Z. Okay? Okay, so let's just digest this a little bit. This is maybe the most unfamiliar part if you haven't seen any of these things before. Okay? So this is a form on a projective space, and you're used to seeing in a form like dx, dy. So what the hell is this weird z sitting there, right? There's a z dz, right? Well, first let's calm down and just compute it to see that it works. Okay? So if I use a coordinate chart where I put z equals 1 little z, then what is this determinant? I mean, this is literally saying I take the determinant of 1 little z and 1 dz, right? So I want to calculate that little determinant. Okay? Which is
0.
Which is no, it's not 0.
You need 0 on the top right.
Oh, sorry, 0. Thank you. Okay. Okay. Because dz is 0 dz. That's what you meant by 0. Sorry. Yeah. And so this is indeed equal to dz. All right? But why am I writing it in this weirdo way? Right? Well, first of all, everything I do, there's nothing. I mean, everything has got to be contracted with epsilon symbols, right? So I can't just write dz. If I have dz, it has an index. So I have to do something with that index. So first, it's not crazy to contract it with z. Okay? So and that's why you see this z dz. But why didn't I see A dz or B dz? I could have contracted those things too. You could say, well, that doesn't look so symmetrical. Well, who cares, right? That symmetrize it. I don't know. That's not a good answer. Okay. There's actually a cool reason it has to be Z dz. And here it's very simple to understand, but when you understand it here, it helps you understand fancier formulas that you run into when you see analogous things in Grassmannians and so on. See, when you have a form on a projective space, remember we said it's very invariant. In a projective space, we have this invariant under Z identified with Tz. Okay? But if I want to have a differential form on a projective space, this is not good enough. You see, each point, here's a point Z, it has its own rescaling. You have a nearby point, it has its own rescaling. Right? In order for a differential form now to be well defined on the projective space, then it has to be invariant, not just under that rescaling where t is global, it's just the number, but where t can depend on z. Okay? So that's very important, that we have not only this global, in this case, GL1 invariance, rescaling invariance, but we actually have to have a local GL1 invariance. And that's pretty non-trivial. Because what does it tell us about dz? Under this local thing, dz goes to t dz, but it also has a piece that looks like z dt. And therefore, anything you do with dz has to be invariant, because I don't want to have this term, right? Anything that I do with dz, it has to be invariant if you shift dz by anything in the direction of z. And that's why any form on a one-dimensional projective space must be proportional to z dz. There's no choice. Okay? It's the z out in front is killing this inhomogeneous piece in the transformation. All right? So that's a very beautiful fact, that any form on a projective space, any form on P1, any one form on P1 in this case is z dz times some function that has weight minus 2 in z. In other words, when you rescale z, it should pick up a factor of t to the minus 2, right? That's the global part. That's the thing that's going to cancel just the overall global part. All right, so once you know that, then the fact that this is the answer, well, first we can verify it, but also we can see there's nothing else we could write down, because that's the piece that's got to be there. Now, the whole point is that we have to have a pole when z hits A and when z hits B, right? So we have to have a ZA and a ZB downstairs. And finally, this thing had to be invariant under rescaling A and B projectively, right? So this has the wrong weights in A and B. So how do I make it have the right weights in A and B? I just write AB. All right? And now that's the only thing it could possibly have been, right? So that's the overall Z dz, and then everything else is fixed by where the poles are and what the weights are. Now let's just check explicitly that it's the right answer. If I put, as we just did, if I put z equals 1z and a equals 1a and b equals 1b, then the z dz is dz. That little ab is b minus a. And these determinants are dutifully z minus a and z minus b. OK? Yes?
Why do we need the local GL1?
Sorry?
Why do we need the local GL1?
The local GL1 is because when I talk about the projective space, by uplifting it to this higher dimension, as I'm doing, by saying that it has this one higher coordinate, there's the rescaling on the point here is totally independent of the rescaling of any other point anywhere. Okay? They're all their own individual lines passing through the origin. So I have to have not just a symmetry under scaling all of them, but under scaling each point above every z separately. Otherwise, it's not a form on the projective space. Okay. And so, so this is our first canonical form with logarithmic singularities. So let me write it down again in various ways so we can. So for this interval, it's z dz AB over ZA ZB. It's also d log ZA over ZB, and so on. Okay? I don't know why I'm being so cruel to you by switching notation so much, because the Z's are normally external data, and I really did it as badly as possible. But I can only quote Howard Georgi, who says, notation should be your slave, not the other way around. So, All right, so now let's move on to another example. So let's do the triangle now. Say we have a triangle in the plane. Now let me switch notation on you. So I'm going to call the vertices Z1, Z2, and Z3, and my point in the space is going to be Y. And now I'm looking for a 2 form. Looking for a 2 form with logarithmic singularities. So what do you think the 2 form is going to be? Okay, this is going to be, now, it's a 2 form, so it has to have 2 dy's. But by exactly the same logic, there has to be dy, dy, y. And there has to be a y there. First, I need it to contract the indices. That's the obvious reason. But secondly, I need it for exactly the same reason as before, that when I do a local GL1 transformation, it has to be correct, right? All right, and now it has to have poles. Now, where does it have to have poles? It has to have poles when y is on the line 1, 2, and 2, 3, and 1, 3. Okay? So,
Why is now y squared dy?
sorry?
Why is now y squared dy?
Well, first of all, y, the y has an index yi, and I runs from 1 to 3. Okay? So y dy, 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 y is all you need to contract all the indices. But from the argument that I told you before, when I do the local GL1 transformation, each one of these dy's picks up an inhomogeneous term that's proportional to y. Just one of the y's is enough to contract with that one and kill it. I don't need 2 y's. Okay? Just a single y is enough. Is that clear? Okay, so in a general projective space, it's always y, dn, y. Right? So you just wedge all the dy's together and add one more y. And you always have that form. So now downstairs, I need to have something of weight 3 in y. And so now let's just write it down. There's a y 1, 2, y 2, 3, y 3, 1. And now I have to make up the weights. And there's only one way of doing it, which is to put a 1, 2, 3 squared. Okay, okay? You guys happy with that? All right, now, this form, so, but let's do another exercise we could have done there, but just to make ourselves happy another way. Let me expand this point y. I can expand it, as some linear combination of 1, 2, and 3. Okay? So let's say I expand y as like z1 plus alpha z2 plus beta z3. Or let me alpha 2 z2 plus alpha 3 z3. Okay? I can always do that. Remember, y is a 3-dimensional vector. So I can expand it as a linear combination of any 3 of them. But it's projective, so I can always rescale one of the coefficients to be 1 if I like. Again, this is not going to cover all of the y space. It's going to cover y's that are somewhere in the corner of this 1. Right? So what are these coordinates alpha 2 and alpha 3 doing? So this point here is alpha 2 and alpha 3 equals 0. Moving along here is going from 1 to 2. So when alpha 2 goes to infinity, this is alpha 2 goes to infinity, hits Z2, and this is moving in alpha 3, and alpha 3 goes to infinity, hits Z3. Is that clear? Is it clear when alpha 2 goes to infinity, this term dominates over the other ones? And again, projectively up to the overall constant, it's like saying y equals Z2. Okay? So this is these coordinates don't cover all of y space, but they cover this vertex, they cover this line, they cover that line. They're not going to do a good job of covering that piece at infinity. Okay? But we'll see all of this. All right? So let's just shove it in and see what we get. So y dy dy. So first let's compute this. Y dy dy is equal to d alpha 2 d alpha 3 times 1, 2, 3. Is that clear? If it isn't, dy is equal to alpha 2 dz2 plus alpha 3 dz3. So dy, fuck. Jesus. Sorry about that. So dy is just d alpha 2 d alpha 3 times the anti-symmetrized product of z2 z3.
You should
Okay.
stress that differentials anti-commute.
Yes, differentials anti-commute. So because the differentials anti-commute, when I multiply d alpha 2 d alpha 3, the other piece has d alpha 3 d alpha 2, and that's what enforces the anti-symmetrization here. Okay. And so finally, when I put y dy dy, because there's a z2 and a z3 here already, these pieces of y don't matter. Will give me 0, so I'll just pick up the 1 piece. And so what I get is d alpha 2, d alpha 3, 1, 2, 3. All right, so that's a little computation for that on the side here. But if we keep going with the form, that's this part. There's a 1, 2, 3 squared. And now, what is y12? Let's compute it down here. y12 is equal to alpha 3, 1, 2, 3. What is y23? y23 is just 1, 2, 3, while y13 is equal to alpha 2, 1, 2, 3. I'm being sloppy with signs here. I apologize. But something to notice is that, as promised, in these coordinates, I can see, interesting things happening with y12 and y13. But y23 is set to a constant in these coordinates, so I cannot see in these coordinates hitting the line 2, 3, right? But I see everything else. All right? So let's shove all of this in, and what do I get? I get alpha 2, alpha 3, and I just get 1, 2, 3 cubed downstairs. And so in the end, I beautifully get d alpha 2 over alpha 2, d alpha 3 over alpha 3. Right? So, as promised, it has logarithmic singularities. But now we see what that means in one higher dimension. In one higher dimension, saying the form has logarithmic singularities means in the neighborhood of every singularity, there's a correct set of coordinates where it locally looks like the wedge of a bunch of d logs with each other. Right? So first, that's the definition of logarithmic. But secondly, it's very important that the form has singularities on and only on the geometry, right? And so in this case, it means that when I take one residue, so this is now a 2 form. So it has, when you write it this way, it looks really simple. I could take a residue near alpha 2 equals 0, for example, right? Setting alpha 2 to 0, what does setting alpha 2 to 0 mean? Setting alpha 2 to 0 means that I put y on the line 1, 3, right? If I set alpha 2 to 0, I put y13 to 0. So I can take a residue where I set alpha 2 to 0, and that means that now y is localized to this line. Now on that line, what is my form? After I take the residue on alpha 2 equals 0, my form is d alpha 3 over alpha 3. This thing has a logarithmic singularity at 0 and at infinity. So now it's a 1 form. Right? But this 1 form has a logarithmic singularity itself. After I took the residue here, there's a singularity here and here at the 2 corners. Okay? So you see this 2 form knows all about the triangle, not just where the edges are, which is obvious from the poles, but also where the vertices are, by further taking residues. Okay, and that's the basic connection. Here it's trivial, but we're in a moment going to see a more non-trivial example. Okay? But the basic connection is that you have a geometry that has, in this case, not very rich, but in more general cases, a rich pattern of faces and edges and vertices and so on, which with various connections of how you can get from a face to an edge to a vertex. And all of that has to be reflected in the pattern of residues that you can take for a form. You have a form, it has logarithmic singularities. You take the first residue, you end up on the face. On that face, it has to have logarithmic singularities corresponding to the edges and so on. Okay? And that's a very non-trivial condition on the form. In fact, it uniquely fixes the form. Okay, so there's a unique differential form that goes along with any polygon or polytope. Now let me show you how it works for a square, and then we will we'll break for lunch. Actually, I'll show you how it works for any polygon, and then I'll tell you. Yeah. All right. So this is now our first non-trivial example. So let's say we have a quadrilateral. Okay, so here's a quadrilateral. 1, 2, 3, 4. I always draw my quadrilaterals so that lines are parallel, nearly parallel to each other, to torture myself. So let me draw this bigger picture. Okay, so here's my quadrilateral. And I want to, that's my positive geometry, the inside of the quadrilateral. And now I want to write down a canonical form that goes along with it. Okay, so let's, and these lines are for later reference, as you'll see. So what could the form be? Now it's still a 2 form. So it's y dy dy. And obviously it has to have poles on all these lines. 1, 2, 2, 3, 3, 4, 4, 1. So I write down y12, y23, y34, y41. Okay? But now I'm not done for a number of reasons. Can anyone tell me one reason I'm not done? One kind of obvious reason I'm not done. Huh? Yes, it has the wrong weight, right? There are 3 y's upstairs, net. There are 4 y's downstairs. So there must be something upstairs, right? Something linear in y upstairs missing. So let me write it down. So there's a y upper I and some line. There's some li upstairs. I don't know what li is at the moment. Okay? Now at least the thing has the right weights, right? But what else is wrong? Well, what's wrong here is that this is making manifest that this form has logarithmic singularities, has poles on 1, 2, 2, 3, 3, 4, 4, 1. But let's say I take the residue where y12 goes to 0. Just like the analog of what we did there for the triangle, right? So if I do that, then that means that now I'm on the line y12. Okay? But on the line y12, now on that line, all of these 3 things can depend on one parameter as they move along on the line. And so, in principle, all 3 of them could go to 0 and give me another pole. Right? What do those correspond to geometrically? They correspond to geometrically, on this line, there's actually 3 places I could naturally have a singularity. Here, here, and also here. Right? So that is the place where 1, 2 intersects 3, 4. Right? Similarly, there's this other bad place where 2, 3 intersects 4, 1. Okay? And so if I do nothing, the form will not have logarithmic singularities only on the quadrilateral. Right? It will also have singularities in these places. Okay? So what do I need to do? That's right. So that tells me who the line is. It's this line. Okay? So I have to choose L to be. And now this is a nice exercise for you in our epsilon gymnastics. But this line is 1, 2 intersect 3, 4, which is a point. 2, 3 intersect 4, 1, which is another point. Right? So the whole thing gives me some downstairs line. All right? So this shows you it's non-trivial, right? It's when I say that I have a 2 form that has logarithmic singularities on and only on, that's a big deal, only on all the boundaries of all codimension, then it's not it puts huge constraints on the form. In fact, for polytopes, you can prove that it really uniquely fixes it. All right, let me actually keep going along this sort of obvious path. And I'm doing it in this case because it just so happens. So this shows you it's a non-trivial problem to find this form. And here what we're doing is just directly using the definition, form with logarithmic singularities, and just putting the numerator down to do the job. Okay? You can do this. We can do this for polygons. We'll just finish it in a moment. Even doing this in this direct way for polytopes in general is non-trivial. Yara and Andrew Hodges and I wrote a not very readable paper on that's Yara's fault, on this. If it sounds like a strange combination of Czech and English, it's not written by me. You can. So it's possible to do, but it's not trivial. It's not trivial to do in this direct brute force way. But let me at least do the one case where it is possible to do directly. So let's keep going to a pentagon. Okay. And sorry, let me be Captain America for the moment. Okay. So let's start with the pentagon. Here's the pentagon that I want. 1, 2, 3, 4, 5. I want the canonical form for that pentagon. So now let's do it again. Omega is y dy dy divided by, and now I have y12, y23, up to y51. And now, what am I missing upstairs? Something of weight 2, right? 2 y's. So I have to have y, y, and some conic upstairs, right? But now, what is the purpose in life of this conic? Well, there are these 5 bad points. This one, that one, that one. That's why I drew them. These are now 5 places where something bad could happen, right? Where I have things that are not actually boundaries of the geometry, okay? But fortunately, there's a conic that passes through only 5 points. So that's the conic. That's C. Okay? And so in this way, you can actually do it for any polygon. Okay? And here in this case, it's simple. This region where the bad stuff happens is outside the polygon, and there's always a curve of the appropriate degree that passes through all of them. Okay? But it shows you that there's, even in this simple case, there's a lot of juice and structure in this idea of associating a canonical form with a certain geometric region.
Every term doesn't cross the interior.
Yes, that's right. Now, in general, the reason it gets harder for higher polytopes in our paper with Andrew is that in higher dimensions, it has to do much more than just kill zeros outside. They can touch. So it never goes inside, but it can touch. And in general, as you take residues, you can even hit double poles and things that aren't even logarithmic. So it has to not just vanish, but vanish to an appropriate degree. And so then you have to do more geometric work and understand the geometry more in order to solve the problem this way. So we did it for the polytopes, for the cyclic polytopes, for the NMHV polytopes. That's what we did in this paper. But doing them that way in general is hard. Okay? So that's just saying, but I wanted you to see in one case with the direct definition what the direct definition is and how you can compute it from the direct definition and how it's non-trivial and interesting. More generally, we have to rely on other things. We have to rely at the moment on various techniques for computing the canonical form. For example, one very nice fact, which is intuitive, even though it's not trivial, is that if you have a complicated region and you triangulate it, you break it up into pieces, then the canonical form for the whole region is the sum of the canonical forms for the subparts. So you can build the canonical form. If you can manage to understand the space by breaking it up into simpler pieces, by triangulating it, then the full canonical form is the sum of the canonical form for the pieces. We'll talk about some of these examples as we move on to discuss the amplituhedron. But I think at this point, you know all the projective geometry you ever need to know. We've gone through a basic example of what positive geometries look like for polytopes and how we can associate canonical forms with them. So we're done with the just background math, and when we come